This is part 1 of lesson 10.4, comparison of series. In this section, we are going to look at two new tests that allow us to compare series for convergence and divergence with ones that are more complicated. So we can look at series we know that are simpler that converge or diverge. And these two tests are called the direct comparison test and the limit comparison test. So let's start with the direct comparison test. So what we're going to look at are two nth terms. So if you let a sub n be 1 over 2 to the n and b sub n be 1 over 2 to the n plus 1, we can see as they're similar, but b sub n is a little more complicated. So if we look at how they're related to each other by writing out the terms, we may notice how we can use these to compare whether or not they converge or diverge. So for 1 over 2 to the n, the first 5 terms would be 1/2, then plus 1/4, plus 1/8, plus 1/16, and then plus 1/32, and so forth. For b sub n, the first term is going to be 1/3, then 1/5, then 1/9, 1/17, and then 1/33. So we can complete statement 3, which says the series a sub n is greater than b sub n for all values of n greater than or equal to 1. And if you notice, hopefully you did already, that a sub n is part of a geometric series, so the sum of that is going to be found by using our little formula, the first term divided by 1 minus r. So in this case, it's going to be 1/2 over 1 minus 1/2. And when you simplify, you get 1/2 over 1/2, which equals 1. So with that, what we can find is that we can conclude that the series of b sub n from 1 to infinity is going to be less than 1, because we can say that the summation of b sub n from 1 to infinity is going to be less than the summation of a sub n from 1 to infinity. And we know this equals 1, so we can conclude that, b sub n, sorry about that, of b sub n has to be less than 1. Okay, so how does the direct comparison test work? It works in this way. Suppose that you have two infinite series with positive terms and that a sub n is greater than 0 but less than or equal to b sub n for all n. So then we can say that if the larger series b sub n converges, then the smaller series converges. And we can look at it the other way too. If the larger series diverges, the smaller series diverges, the larger series has to diverge. So, saying that in words, if you think the series converges, then compare it to a converging series. The series you compare it to should be larger, because if all your terms on a graph are below the one that converges, then the one below the graph is kind of limited by that upper series, so it also has to converge. And the converse thinking is true too. If you think a series diverges, compare it to a series that is below it, because if the series on the graph below it diverges, how could a series that sits above it on the graph converge? It also has to diverge. So that's what we're going to do now. We're going to look at some different series that are a little more complicated than we've been looking at and see whether they converge or diverge. In example 1, we're going to determine whether the following series converge or diverge by using the direct comparison test. So what I want to do for letter A is notice that this looks a lot like this part right here. Looks a lot like at 1 over n to the 1/3. So I'm going to compare it to that series. So what I can notice is that 7 over n to the 1/3 is always going to be greater than 1 over n to the 1/3 for all n greater than 1. And the other thing I want to notice, and the reason why I picked that series, is that the summation from 1 to infinity of 1 over n to the 1/3 is a divergent p-series. And p is equal to 1/3, which is less than 1, so that's why it diverges. So what I can say is, therefore, my given series diverges. By the direct comparison test. All right, for letter B then, if you notice, if we just ignore the +1, we kind of have a geometric series here. I'm just going to not be super formal and not put the limits of integration there, but you can if you want. So we have a geometric p-series, and what we can also notice is that this series term is always going to be less than my 2 over 3 to the n. Those terms are always going to be smaller for all n greater than 1. So I can say that my comparison series converges since r equals 2/3, which is less than 1. Therefore, my given series converges. By the direct comparison test. Okay, next example. What makes these hard is trying to figure out what to compare them to. So the first two I thought were a little easy. The next one might be a little more difficult because you have an n in the numerator and an n in the denominator. But if you sort of divide these, what we can do is we can compare them just like 1 over n squared. If you were to try to simplify the n's, and that's going to be our b sub n. So now what we can say is that, and if you want to, you can check the terms if you're not sure. So you can start writing them out. So what you have is that a sub n is going to equal 0 I'm sorry, it's not going to equal 0. Yeah, it's going to equal 0 for the first term. And then the second term is going to be 1/11th, and then 2/30ths, and then 3 over 67, so on. And with your b sub n's, you're going to get 1/4, then you're going to get 1/9, and then 1/16. And what you can see all the time is that your a sub n is less than your b sub n. And that's for all ends, and that's for all of them, greater than or equal to 1. So then what we can say is this series is a convergent p-series. And if you want, you can make sure you put p is greater than 1 and p equals 2. Therefore, our given series converges. So the next one is very similar to that one. So what you can look at for letter D is the idea that you have an x squared or an n squared over an n cubed, which leads you to 1 over n, and that's going to be your b sub n. And what we're going to notice here again, since these are a little more complicated, it does help to write out your terms. So the first term for the given series is going to be 9, and then we're going to have 33 over 15, and then 73 over 53, and so on. And our b sub n's, and we want to see if they're bigger or smaller, we have 1, then we have 1/2, and 1/3. And what you're going to notice is the first term in our a sub n is 9. That's a lot bigger. And the second term is more than 1, and so is the third term. But in our b sub n, we're at 1, and then we're at less than 1 for each of these. So we can definitely see that in this case, a sub n is greater than b sub n. And why that's a good thing, and that's for all n's greater than or equal to 1, we know that we have the harmonic series here. And we know that the harmonic series diverges. Then we can say that our given series diverges. And that is by the direct comparison test again. All right. The problem is, though, and this is one reason why we have so many tests, is it possible for these tests to fail? So here's an example where it does fail. So let's go ahead and write out the terms for both our a sub n and our b sub n. So for a sub n, we have 1, and then we're going to add to that 1/3, and then 1/7, and then 1/15, and then the fifth term is 1/31, and so on and so forth. And for b sub n, we have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so forth. And so what do you notice is that the a sub n terms are greater than the b sub n terms. So will the series converge? The problem is that the terms are so close together that we cannot be sure. Because they are so close. So the value of the terms are close in value, I already said value. but the one we're trying to figure out is greater than that one, so you can't be so sure. So what do? So we have other tests, and what I'm going to do in the second part of this video, the second video, is talk about the limit comparison test.